So we are talking about sequence modeling. So we have finished the imaging problems, and with MobileNet V2, we'll probably do one more transformers, right? Vision transformers. Then we are almost all done with the vision imaging problems, right? So now you can do object detection, you can do face recognition, everything you can do, right? You have all the necessary background to do that, right? Just build a CNN, you use all the optimization tricks, pick a suitable architecture, and then do it. Any questions on that so far? No? Okay. So we're talking about sequence modeling, and we talked about multiple scenarios where, we looked at this example where, why a conventional neural network may not work in sequence modeling, because these words that come, these words and these phrases, they co-occur very frequently, but their position in the sentence need not be fixed. So for different examples, you will get the same pairs of words in different positions. Now, if you just train a vanilla neural network using that, or even a deep network using that, then the words like, here the World Cup, you will have to learn at different neuronal levels, different weights at different neuronal levels. You have to somehow incorporate that. And that is not scalable. That does not really work. So the solution to this is what has been designed earlier, which are called the recurrent neural networks. So they are, in some sense, they work with sequences, but they are in some sense very similar to convolutional neural networks, because in convolutional neural networks, the convolution kernel, you are sharing the weights across different features of the input. In this case, the image, across different image positions. But here, we are sharing the weights across the time. So you're given a sequence, the sequence comes in, you learn some weights, but these weights are shared across the temporal ordering of the sequence. And you can adopt it to all kind of predictions. You can do a sequence input, single output. You can do single input, sequence output, and then sequence input and sequence output. So all those three different variations that we discussed, you can also do with the RNNs in a much natural manner. But before we go to RNNs, what is the most used model for the sequences, right? For time series data, and they are called autoregressive models. And here you have some signal S, which is a function of time. I'm representing it time as a superscript. And think of this S as a real valued number, right? A real valued signal. So I'm speaking to you, my voice is getting recorded. You can think of that speech as a single signal, right? If it's a mono speech, then you get a time point, at every time point, you get a value. And my sampling rate could be 44 kilohertz, so I get a bunch of values, 44,000 in a second, and that is my S of t plus 1. How do I model it? It's some alpha times S of t. Alpha is a scalar, plus some error. Very simple model. The next time step is alpha times the previous time step. And, we can generalize it also. We can say that S of t plus 1 is summation alpha tau. Tau is going from, let's say, 1 to some lag L. S of t minus tau, you can make tau go from 0, right, plus epsilon t. Okay? So what you see here is model of order 1. We are looking at one time step in the past, and based on that we are doing a prediction of the future. Right? Here what I have is a model of order L plus 1, right? Tau is going from 0 to L. Right? So I'm looking at the previous step, a step before that, a step before that, and so on, up till L steps before, L plus 1 steps before, and finding different coefficients here. So what are my model coefficients? What are my model parameters? Alphas, right? So for a single step autoregressive model, order 1, I have a single parameter alpha. For a L step, I have L parameters, alphas, right? L integers. I can also think about vector autoregressive models, where my signal is now a vector. S is a vector of m dimensions. And it is some matrix A times S of t. And the matrix A is m cross n. So I look at the previous time step, and then based on that, I make a prediction of the next time step. My prediction is just A times S of t. So you can think of S of t as, let's say, bunch of stock signals, right? Prices of the stocks at different days. So t could be your day, S of t could be, the price of the stock. You can look at maybe the opening price, the closing price, and all. You put all of that in the vector form, and that is S of t. And the matrix A that you are learning, which is, based on the past, how do you predict the future?
So the order of L plus 1 is like, it combines a lot of previous words together, right?
Yes. L plus 1 is like, a lot of previous time steps together. You can think of also this as a speech, a text. So if I have a text, I have a sequence of words. Each word I can represent using a vector. We talked about one hot encoding. So I can create a dictionary, and then each word I can represent as either a 0 or a 1 vector. It's just like only one component would be 1. And that's my S of t plus 1. And my task is to predict the next word in the sentence based on the past words. And that again can be modeled as a vector autoregressive model. So those are the conventional models that have been used very much in signal processing. Even today, when we talk about designing communication systems, we often get across these kinds of models. But and there's a lot of theory. You can spend your life doing that. Not only course, you can still do a PhD on this. Okay, but we are not going to go into much more detail. These are all linear models, right? Linear autoregressive models, because this matrix multiplication is a linear operator. Okay, and this is also a linear operator. You can also do vector autoregressive model with a moving average. So here epsilon also you can think of it, the average of the past k values of the noise. So that is called a ARMA model. You can also look at a differential of the current signal. So S of t plus 1 minus S of t. And then use that, predict that. And that is ARIMA model, right? So there are various variations of this. You can look at any time series modeling book, and all of these would be there. And signals and systems will also talk about it. But here we try to generalize it even further. So this is how we represent a general dynamical system. Okay? So it has a particular state, and that state evolves as we progress in time. Okay? So let's say S of t plus 1 is a state at time t plus 1. The next state is a function of the previous state and the model parameters. If it's an autoregressive system, then this f of S of t for, let's say, AR1 systems, this would be a alpha times. So f is alpha times, or how do I write it? Okay, I can write it f of S of t comma alpha, or semicolon alpha is alpha times S of t. Okay? That's the AR1 system. Okay? But you can think of more general functions, and the state S need not be a scalar; it can be a vector. So you can have, you can embed many more complicated things in the state. Okay, and these thetas are your model parameters. Okay, and what is S of t is the previous state. And this is your next state. Okay? And this f is your model. Okay? So if I specified the f, as in this case here, then my model becomes an AR1 model. And now my model parameters are only alpha, only one parameter to learn. But I can define a more general function. Right? You can think of any mathematical function, but what we are going to do here in the context of deep learning is we are going to define this using a neural network architecture. And that fixes my model. So that's my model. This F is my model. And then the parameters would be the weights of my neural network. And that's those are parameters I'm going to learn by looking at this. Okay? So this step is clear. Any questions on anybody so far? This part is clear? Okay. Now I can also think of a dynamical system which takes an input. Right now we talked about in the previous slide, here's a dynamical system, it is evolving on its own. There is no input, there is no output. But what if we give some input to the system? So we can model it as, here you can see the evolution of the states. This is the time. You start with some state s of t minus 1. The next step you go to state s of t. But along with s of t you have some input which is x of t. So this is your input. This is your state. Okay? Now, given the present state, given the input, using these two, I come to the next state. And that is my function f now. So how do I get the f next state? The previous state, the input, and the model parameters. Then I get to the next state. So in the AR1 example, I can think of epsilon t as my state, for example. Right? For epsilon t as my input. So then I can go to next state using that. But in general, it's going to be much more complicated than that. Okay? This is clear? Okay. So, this representation I can represent in a very compact manner. Instead of putting it like this, the way I represent it is I make a square dot. Right? So x is my input here. Here is my hidden state or my state of the system. And the moment I just put a self loop with a black dot or black square, it means that this feedback is delayed by one time step. Okay? So what does this mean? This h is a function of x. Right? This arrow also means h is a function of h. But I put a square here, which means it's a function of h at the previous time step. Okay? So if I unfold this, I get the exact same, recurrence that I had before, the same system that I had shown before, which is, at any point in time, h of t minus 1. From there, how do you go to h of t? You apply the function f to h of t minus 1 and x of t minus 1 to h of x of t, and you get to the next state. So h of t plus 1 is a function of the previous state and the current input and the model parameters. Okay? Huh? No, so this is x of t, this is h of t plus 1, right? So, yeah. Okay? So, what I have done is, basically just put a recurrence where you are dependent on the previous state. Now, this function f is going to be a neural network. And how do I define that neural network? Yeah. So, this is clear. This is a very important step. We will spend more time if there's something which is sort of not clear. Everybody is on board?
Yes.
Huh? Okay, wonderful. So now, what is a recurrent neural network? This is a general architecture of the recurrent neural network. It has an input x. It has a state which we represent as h. It has an output which we represent as o. And then finally we have a loss function L. And then their labels. So right now in this example, what we are going to assume that for every time step in the input is a sequence. Right? So you can have x0, x1, x2, x3, x4, and corresponding to that input there is also an output. So we are doing a sequence to sequence neural network where the output length is exactly the same as the input length. So every input there is an output, except that it also depends on the previous values. So here is x, my input. Here is y, which is the corresponding output to the labeled data. What will be the example here? An example will be a sequence of x's and y's. The sequences could be of any length. It could be length 1, it could be length 2, it could be length 5 or 10 or 15. So different examples could have different sequence length, but each example is a sequence of x and a sequence of y of the same length. Okay? So an example is a sequence x comma y, or let's say, I can just write it as xt comma yt, and this is the ith example, so I'll just subscript with I such that I is going from 1 to, what's my sequence length? No, sorry, t is going from 1 to some tau I. That's my sequence length. Right? So that's my example, and I'm given multiple such examples to train on. And once I've given multiple such examples, I'm going to train on it and I'm going to learn my weights. So this is clear, an example. And different examples could be of different lengths, because tau i's are the length of example I, and that could be different for different examples. Okay? Now, from the input, how do I get to the state h? What is the function that determines the next state from the next input and the previous state, right? And this function is given by this recurrence here. Okay? So let's unfold this. So what this essentially means, that you had some state previously. At time step t minus 1, your input is xt minus 1, and your hidden state becomes, your state becomes h of t minus 1. And let's think of these as a single layered, fully connected neural network. Okay? So what do I mean by that? So let's see. Yeah. Oops. Sorry, yeah. So U are the set of weights that are actually going to determine how I calculate the state h of t minus 1 along with the weights w. Okay? So let's say my x, I, t is a vector in some m dimensional spaces. My hidden state h of t is another vector in, let's call this m1, let's call this m2 for lack of any better word. Okay? m1 need not be equal to m2, m2 could be different than m1. Okay? So, what is my h of t? H of t is a function of x of t minus 1. So, this is u transpose x of t minus 1 plus w transpose ht minus 1. That should be xt. Xt, thank you. Yes, you are right. Xt plus w transpose plus a bias term. Okay? Okay. And so w of ht minus 1, u of xt plus bias, and the sigmoid function g. Right? G could be any activation function. We can do sigmoid or tan h or relu, whatever you want to train with. Okay? So this tells me how to get the state. Now how do I get my outputs? Your output is a function of the state. So O of t minus 1 is V transpose, or let's say V only, if you're using V notation here, plus the bias C. Okay? And your final output, y hat t, you can apply the softmax on O of t. Okay? And your y could be of the size, so yeah, y hat t could be of the size r to the m3. Okay? You could be outputting, a multi-class classification, so it's a vector of that size. So what is my model size? What's my model size? What is the size of U? R of M1 cross M2. Okay. How about W? Is R of M2 cross M2. And my output V, M2 cross M3. So these three matrices plus we have a vector B, which is R of M2, and C, which is also R of M2. Yeah. C is R of M3. Thank you. Yes. Yes. Yeah. Okay. So that specifies my recurrent neural network fully. Right? I have the models. I have the model. This is my model. I have my model parameters. And I have told you how to get y hat from the inputs. Right? Now, how do I compute the loss now? So this is going to give me y hat. And I already have, because I assume my y is the same size as the input x. So for every step in my input, I have its corresponding output. So I have this from the labels, right? Y of t minus 1. This is available from the labels. Okay? So I can apply the simple loss, cross entropy loss, or if it's a prediction problem, if it's a regression problem, I can apply the squared error or absolute error, whatever loss I have. So I can actually compute my loss at time t minus 1. Similarly, I can compute my loss at time t for the output at time t. Similarly, I can compute loss at time t plus 1 by comparing these two values, y of t plus 1 and y hat of t plus 1. Okay, and so on. So at every time step in the recurrent neural network, I can create the loss. My total loss, L, I can write it as summation. T is going from 1 to, let's say, tau I, L of T. Right? So I just sum these losses over the entire sequence that I get for the loss of the ith example. And then I sum over all the examples, I get the total loss. Okay. Yeah.
Is YT a single label or a vector?
YT depends. If it's just a binary classification problem, then it will be a single. But if it's a multi-class classification at every step, then it could be a vector. So for example, you could be given a sentence and your job could be to tell whether each word is a noun or a verb or a pronoun or an abstract noun and so on and so forth. Right? So in that case, your y would become a vector.
So it's a one-hot encoded.
Huh?
It's a one-hot encoded vector.
It's a one-hot encoded in this particular case, yes. You could also have some kind of, regression problems. Right? So in that case, it could be just a single number. So this is a fairly general framework. You can have, depending upon the problem that you're solving, you can choose your yi's could be different.
The translation will be a regressive task, right? Like from one language to another language, that will be a regressive task.
No. You will be given some examples, right? An example text in one language and the corresponding translation in the other language.
So what kind of verb would you use there?
You would use some kind of cross entropy loss. But wait, so we have not talked about the word embeddings yet, right? So if you are just doing one hot encoding, then it would be a cross entropy. But if you are doing a word embedding, you are representing the word as a vector, and then you would use a squared error kind of a loss. Okay? So that's all there is to RNNs. That's all there is. Now, all the other mathematics we have already done. So now what's the next question? What's the next? How to train the network? How do you learn this network, right? How do I learn the weights optimally? So I have to do a back propagation, right? So for that, what do I need to do? How to learn? So for this I need to compute del L by del U, del L by del W, del L by del V, okay? And del L by del B, and then del L by del C. Right? So I have to compute all these things, right? These are my model parameters. And if I know how to find the derivative of the loss with respect to these parameters, then I can do what I always do, which is kind of gradient descent, and then I can apply all the techniques that we've learned to sort of make it faster. You can do stochastic gradient descent, batch gradient descent, and everything else. Okay. So now the question is, how do I calculate the derivative of loss? Okay. But before we go there, now you see, we talked about this problem of, World Cup. Now you see these weights, U's and W's, they are shared across the time. So, you put a word here and it leads to learning of some weights here. Then you put the next word here, the same weight is there at every time step. So different time steps, the U's and the V's and the W's are the same. Right? So whatever you learn at every time step, you sort of update U's there. So if there is a phrase which is kind of coming together, then you don't have to get its impact on different types of weights in different units. All of this is encapsulated right here in these U, V's and W's. So that's something which is sort of, and in some sense it is similar to CNNs in the imaging problems, because in CNNs also across the space you have these weights, convolutional weights, which are shared. Right? And this reduces the capacity of the network. But it improves the generalizability, because then you don't have to learn it separately. And these RNNs are still very powerful, because we're not talking about deep networks here. You can actually think of this U as a deep network, right? It need not be just a single step neural network. You can also think of a deeper network here. And similarly from here, H to H, you can think of it as a deeper network, right? A more deeper architecture. And from here to here also you can think of deeper architectures. But for now we just kept it at a single step architecture, right? Single layer architecture here. Now it turns out that they are still very powerful. You can get to the reference from the Godfrey book, talks about if we do not restrict the hidden state, if they have infinite precision, so you can represent arbitrary precision numbers there, then essentially what you can do is you can stimulate a stack with the H. So for example here, you want to push a number on the stack, you can push a bit in the stack, you can just sort of divide H by 2 and then add 1 or 0 there. So you can do those kind of operations here just with mathematical operations, because H is in the model, they assume that H is infinite precision, and what they showed was that these recurrent neural networks can emulate any Turing machine. That is what they showed. So although this is a very unrealistic assumption, we don't have unlimited precisions. We only have 32 or 64 bit precisions, and we also try to reduce it to just 4 bits to get speed ups. But at least theoretically, if you can get large precisions, then they can actually simulate a Turing machine, which is kind of interesting result. So they can be very powerful. That's what the point is, even without going deeper in the recurrent neural networks. Okay? Yeah. So we use mini batch of examples. Yes?
It has been proven that they can simulate Turing machine, like if you go deeper.
No. Even without going deeper, if you have unlimited precision, you can simulate Turing machine. That's what we're saying. Okay? So now, so we use mini batch of examples, unfold the computation graph, backpropagate the loss, use the chain rule, and you can use any of the standard gradient learning algorithms. Okay? So let's work it out. It is also called backpropagation through time. And why is it? So let's look at it. So your total loss is, let's look at one example only, right? Loss for one example. So it's summation of L superscript T, and T is going from, let's say, 1 to tau. Okay, so that's your sequence length. So I want to find del L by, let's say, del W. Okay, so this would be summation I is going from 1 to tau, del of Li, or rather, okay, maybe I should use T. T is going from 1 to tau, so this will become del of L of T by del W. Okay, it's a simple linear thing, right? Total loss is this. Now what is del of L T by del W? Okay, so I can look at the last layer when T equal to tau. Okay, so let's pretend that this is L of tau, this is Y of tau. So it will be some function of y hat and y of tau, right? Last step. Okay, so this is L of tau. So I can find del of this function. So should we take it more concrete, or should I go to general function f here? Because let me just make it cross entropy here, right? This is a cross entropy, CE, let's say cross entropy between this, right? So then this is del of cross entropy y hat tau and y tau by del of y hat tau, right? So this is a standard cross entropy derivative that you can calculate. Okay, then I have to multiply it with del of y hat tau with respect to del of output O of tau. Sorry for this. This is tau here, not T. And this is softmax, right? So this also we know how to do, into del of output at tau with respect to h tau. And how is output dependent on h? So O tau is, let's go back, VH transpose plus C. So VH tau, V transpose H tau plus C, or in other words, I've just used V here, not V transpose, okay? Okay? So, see this Y tau and O tau, there's a one-to-one relationship there, right? It's a cross entropy. So, this will become a diagonal matrix. Here this would become a matrix, right? Output is, Now I need to find, so this you can find it, this is V only, right? Then you need to find del of H tau with respect to del of W. Okay? And what is the equation for H tau? G of WH plus u of xt plus b, okay? So g of w h tau minus 1 plus u of x tau plus b. Okay? So this w comes here, right? So you can find, right? So this is so this you can again find, this is g into 1 minus g, right? If it's a standard, sigmoid activation function. And then you can find the derivative with respect to w. Okay? But are we done yet? Or we are not done? Huh? We have to find?
With respect to u.
No, but I want to find with respect to w only. So is it done? So am I done when I do this? Huh?
Yes, because ht minus 1 is already computed.
Because st minus 1 is already computed. Huh? ht minus 1 also depends on w. So ht depends on w in this particular way, but ht minus 1 is also a function of w.
But sir, we keep ht minus 1 fixed when we are differentiating with respect to w.
No, so this is a function, right? You are sort of, it's like, think of it as if it's a function like this, right? So let's say f of x is equal to x squared. No, wait. So I want to find f of w, right? I want to find derivative with respect to w. Let's say f w is equal to w squared plus g of w times w cube. Right? So I can take the derivative with respect to w square and put it here, that's fine. I can take that, apply that, the multiplicative rule here. I can take derivative with respect to w cube, but I also have to take derivative with respect to g of w, because this is also a function of w. Right? So similarly, here h is a function of w. So I can apply the multiplication rule. So I can, take h fixed and take derivative with respect to w. I'll get one term. But then the second will be keep w fixed and take the derivative with respect to h. h tau minus 1. So del h tau by del w, assuming, so this will have two parts, assuming fixed h tau minus 1, and then also compute del of h tau minus 1 by del w. So that's a very critical step. So again, it is similar to the neural networks. We look at, back propagating in the neural networks, we are finding derivative with respect to a weight. So your output activations depend on those weights, and every activation depends on those weights. So here, if you think about this term here depends on the weight, this term also depends on the weight. So if both these terms depend on the weight, and I want to find the derivative of this with respect to the weights, I apply the multiplicative rule. So it will be derivative times weight plus keep this fixed and find the derivative of this with respect to the weight. Okay? Okay. So, and now how do I find derivative of ht minus 1 with respect to weights? I have this ht minus 1, h tau minus 1 or whatever, Now you can see that it depends, I mean, yeah. So, it depends on xt minus 1, it depends on ht minus 2 through these weights w. So you can again do the one more step and do the back propagation, like just exactly like that what we have done in the deep networks. And this is what is essentially called the back propagation through time. So we have losses, and it is some of these losses. So these losses will back propagate here, and from here they will come here, and then from here you'll have to back propagate here, because you have to find del h of t minus 1 with respect to del of ht. And then del of ht by del of w, and similarly del of ht with respect to del of ht minus 1. So, so simply think of this unfolded neural network as just one neural network, and then you find the derivatives, except that now the weights across different layers are shared. Weights are not only shared within the layer but outside the layer also, because this w is same as w in the next layer. And then there are losses here also. Okay? So this we already talked about. Yeah, so LT, we just look at the loss as the sum of those losses. Yeah, so we talked about del L by del W. Do you want to work it out? The exact formula? And the same method you can find del L by del V. Right? So what is del L by del V? You back propagate it, here you will find it. But this also depends on ht minus 1. Right? But this h minus 1 does not depend on V. Right? So I think we will be done with this step. Except for we have to do it for all the steps here, right? This is LT minus 1 and all of that. Okay? Del L by del U, it depends on this. So you can back propagate all the way here. But ht plus 1 also depends on U through xt. So, okay, so let's see. Can we write it now? Let's see. Del L by del W is first summation. We are only doing for one example, then we can add it up for all the examples. So, summation t equal to 1 to tau del L of t by del h of t. Okay? Plus del of h of t with respect to h of t minus 1 into del of h t minus 1 over del w. Right? Plus del of ht minus 1 del of ht minus 1 over del of h t minus 2 into del of h t minus 2 by del w, and so on. Right? And these will be simply matrices. So all the way till h1, right? You can get all the way to h1. And you can see that, these are just getting matrix multiplied. So how do I find del of ht with respect to the previous layer? Right? That's also simple, right? That's again w only. W or W transpose? Which one? So h of t equal to g of W h of t minus 1 plus u of xt plus b, right? So del of ht over del of h t minus 1 is g of this thing into 1 minus g of this thing into what? W or W transpose? You have to tell me. Huh? W? Where, this term is here. Okay. So why don't we work it out, okay? Maybe we can, I don't have time. But maybe next time we'll have a quiz on this in class. We'll work out the formulas, right? Del L by del V. I think del L by del V is simpler, right? Del L by del U is going to be more complicated. Okay, so what is del L by del V? Is summation T is going from 1 to tau del L by del L of T by del V. Now del of LT by del V equal to so what is my LT? Cross entropy of softmax OT and YT. Yeah. So now you can work it out. Del L by del U, you'll have to back propagate through time all the way. Right? So this is what is called back propagation through time. So I'll just leave it for you to work out, and then maybe we'll just do it very quickly in the class in 5-10 minutes maybe. I mean, not in the class, in the quiz maybe. And so we left out B, but B is again can be done in a very similar manner, right? And the C also you can do it in a similar manner. Okay. So yes, so this has been very successful. RNNs have been very successful in sequence modeling, even before deep learning came in. And I think in speech they were very, very, very useful. Speech processing, speech recognition, automated speech recognition, and all. Earlier they used what is called a hidden Markov models, right? Autoregressive models and hidden Markov models. But with with RNNs and then LSTMs, they found much better. So they have been extremely well utilized there. So we'll cover it very briefly. We'll not go into much more detail because the future papers, there's a paper called Attention is All You Need, right, that you're going to present. They actually tell you that you don't need RNNs. You can just do it with attention only. So there's a mechanism called attention that they discovered, invented, and with that it kind of transformed the field of deep learning. So, But anyway, I think we'll cover the little bit more detail. We'll talk about LSTMs. We'll talk about few issues in training RNNs and then how they encountered, how they solve those issues. Then we move to more advanced topics. Unless you want to cover RNNs in more detail. Huh? Okay, so we'll stop here. We'll see you on see you on Monday. And who is present?